I thought it would be a good idea to take a moment to summarize all of the concepts that we just discussed involving the deviations from Raoults' law. So let's take a look at that. We'll take a look at three different cases here, starting with the case of a negative deviation from Raoults' law. You have a negative deviation from Raoults' law when the vapor pressure of the solution is lower than expected. And the reason why the vapor pressure of the solution is lower than expected is because the IMFs in the solution are strong. So we'll say strong IMFs in solution. Now, because the IMFs in the solution are strong, when you form the solution, it will be more stable. It will be lower in energy than the pure solute and the pure solvent. And so the delta H of the solution will be negative. This will be a process that is exothermic. An example of that might be if you were mixing together acetone and water. We saw that earlier. So we'll just draw that in here. All right, so there's our example of mixing acetone and water. And I'll remind you that the reason why we end up with a negative deviation from Raoults' law and stronger IMFs in the solution is because in acetone, you do not have hydrogen bonding when it's by itself. But when you mix it with water, acetone now can participate in hydrogen bonding because you have the donor from the H in water pairing up with the acceptor, that is the O that's in the acetone. Now, because the solution formation process is exothermic, it's going to release energy. And if it releases energy, then the solution and the surroundings are going to feel warm. What about if you have a positive deviation from Raoults' law? Well, the reason why you have a positive deviation from Raoults' law is because the vapor pressure of the solution is higher than expected. And the reason why the vapor pressure is higher than expected is because the IMFs are weak. If the IMFs in the solution are weak, then the solution is more unstable, or it's higher in energy than the pure solute and pure solvent. And so the delta H for solution formation will be positive. This is endothermic. An example of that might be the mixing of benzene and water. So we'll go ahead and draw that. And we talked about why that was the case here, because benzene is totally nonpolar and cannot participate in hydrogen bonding interactions at all. It can't participate in dipole-dipole interactions either. And so when you try to mix it with water, it's not going to interact very well with the water. And it's just going to prevent water molecules from being able to do hydrogen bonding with other water molecules. So that's pretty unfavorable. Now, because the process is endothermic here, that means that the formation of the solution will consume energy, and that will make it feel cold because heat is being consumed. Lastly, we'll talk about what happens when there's no deviation from Raoults' law, meaning that you have an ideal solution. So when you have an ideal solution, then that means that the vapor pressure of the solution will be exactly what you expect. Or another way of saying that is that the solution obeys Raoults' law. In terms of the IMFs, in an ideal solution, the IMFs in the pure solute, the pure solvent, and the solution are all the same. And because the IMFs are the same in the pure solute, pure solvent, and the solution, then that means that the process of making the solution is going to be energetically neutral. It's neither exothermic nor endothermic. The delta H will be exactly equal to 0 because the solution has the same energy as the pure solute and pure solvent. They're equally stable. Now, an example of that would be if you were to mix two molecules together that have the same IMFs. Maybe we could take a look at the mixing of benzene and toluene, and I'll draw out those two structures here really quick. All right, so there's our benzene, and then toluene is the exact same molecule, except one of the H's is replaced with a carbon and 3 hydrogens. So we'll go ahead and put that in here if I can fit it. All right, and there we have it, right? The same molecule, except just replace the H with a CH3 group, just like that. That's benzene up here and toluene down there. Now, in this case, right, because they're all just London dispersion forces, they're all totally nonpolar, and that's it. when they're mixed together, there's going to be the same IMFs in the pure solute and pure solvent as what you have in the solution, right? And so that is why we would say this could be assumed to be an ideal solution. And because the delta H for forming the solution is equal to 0, then that means that the process of making the solution does not consume heat and it doesn't produce heat either. And so that means that the solution will neither feel warm nor cold. The solution will remain the same temperature. And that's it. That summarizes everything that we've discussed in terms of the deviations from Raoults' law. I think it's nice to have a table like this that kind of compiles all of the information into one place and makes it a little bit easier for you to look back on. I do think that the concept of the deviations from Raoults' law can be a little bit overwhelming at first because there's so much going on, and that's why I thought it would be a nice idea to organize everything here to make it seem a little bit more accessible and to show how all of the information can be related here. One more thing that might be nice to do here is to just use an analogy that has nothing to do with chemistry to kind of explain what's going on here. So in this analogy, instead of talking about molecules, we're going to talk about people at a party. Okay, so let's say that I'm at a party. Think of the party as being like the solution. And if I leave the party, then that's like the equivalent of molecules leaving from the solution phase and going into the gas phase, right? So the more susceptible I am to leaving, right, the higher the vapor pressure would be. That's kind of the analogy there. So let's say that I'm at this party and all of a sudden a group of really good friends of mine that I haven't seen for a long time comes in. These are people that I get along with really well. So we have pretty strong IMFs when we're together in the solution. We really enjoy each other's company. And by them coming into the party, I'm more likely to stay at the party for longer, right? So that's another way of saying vapor pressure of the solution is going to be lower than what you expect. I'm going to stay in the solution. I'm going to stay at the party for longer than you would expect. Now, let's say that I were at the party and someone I really disliked suddenly showed up. Someone that I don't get along with very well, right? Like when you mix benzene and water together, they don't like each other. And they have very weak intermolecular forces. And if one of my enemies comes to a party, I have pretty weak interactions with them. And because of that, as soon as they show up, I want to get out of there, right? I'm going to leave the party, which is like the molecules leaving the solution and going into the gas phase. The vapor pressure of the solution, therefore, would be higher than what you expect. And let's say that we're at a party and more people who are just like me show up, right? Maybe it's like other faculty in the chemistry department. They're people that I'm like kind of friends with, but I'm like work friends with them, right? Like I like hanging out with them, but it's not like if one of my best friends shows up, I'm happy to stay and continue to be at the party and hanging out with them, but nothing significant is really going to change in terms of my propensity to stay or leave the party, right? And so that would be like the situation of an ideal solution where there's no real change in the vapor pressure of the solution or how likely I would be to leave the party in that case. Sometimes I think it's nice to hear an analogy that has nothing to do with chemistry, and hopefully that can also help you to visualize what's going on here. And that brings us to the end of chapter 17. So I recommend taking a look at this slide to see all of the concepts that we discussed here in this chapter and, use this as a study guide if you'd like. And up next, we're going to start chapter 19.